You see that? You see that chunk of ice just there? That is a piece of the Larsen ice shelf, which my friend Sammy works on, and she's never been to Antarctica. She's been to the Arctic. However, she has worked on the mathematical modeling of why the ice shelf is melting, and I think I'll send her a picture. Unrelated to this specific video, I'm going to be in Los Angeles in early January 2024 and doing a live show, an evening of unnecessary details. So if you're nearby, there are details in the description below. Check them out. If you're somewhere else in space or time, I'm always doing shows. Links below. So I'm here now with my friend Sammy, and you did get the selfie of me with the ice shelf.
I did.
Yes, and you were
quite salty.
You were a little upset, if I remember correctly.
Yes, I have been studying Antarctica for some years now.
Yep.
And I have not been there yet. And you went and you saw my ice shelf.
When I got on the ship, I was like, I have to see the Larsen ice shelf. See. I thought it'd be really nice just to go through why your mathematical work on the ice shelf is both so interesting and so useful. And that is why we happen to have 2 glasses of ice water that we are deliberately not drinking.
Yeah,
I think we're gonna mark the level. That's what we're gonna do.
Some life science here.
Oh yeah, this is working. This is fine. Oh no, I spoke too soon. I think if I dry it and then draw really quickly. Oh, look at that. There we are.
Okay.
There's the line. So when I was like, hey, do you want to come and have a chat, talk about your research? I specifically said, would you like to talk about your paper, which just off the top of my head was called A Mathematical Model of Melt Lake Development on an Ice Shelf.
Which is very exciting.
Specifically,
people very rarely asked to talk about this paper.
Really?
There's loads of maths in it.
Such a good paper.
Yeah, I know. I think so.
I actually said, I went through all your publications, and I was like, this was my favorite, specifically figure 2. So we'll put that on the screen now. So this is figure 2 from the diagram, which maybe I'm very excited about. You said you got nicer versions of that figure?
Yeah, well, I have ones that show the actual equation. This one is just kind of showing overall how all the equations fit together. But
yeah.
Yes, this paper is looking at lakes on top of the Larsen C ice shelf.
Right.
So Larsen C is in the Antarctic Peninsula, and we're interested in that for several reasons, but one of them is that Larsen A and B, because there were A and B.
Yeah, I didn't see them.
You did not, because they are pretty much no longer there. So Larsen B had a very dramatic collapse back in 2002. The area of the ice that was lost was about twice the size of Greater London, so a huge amount of ice that was lost.
It's like over 3,000 square kilometers of ice.
Yes. Yeah, like within a
Gone.
month, the ice shelf just shattered and the ice all floated away.
Yep.
And where the ice that's flowing off the land in Antarctica hits the ocean, it just keeps going.
Just out across the water.
Exactly. And those kind of big floating sort of tongues of ice that stick out from Antarctica, we call those ice shelves.
But I guess it's building up again now, there's that.
Well, what's happening now is that the glaciers that used to feed onto the Larsen B ice shelf can now just go straight into the ocean.
Right.
So instead of the ice shelf rebuilding, we're just dumping lots of ice into the ocean.
Oh, okay.
From those glaciers. But the thing with Larsen B is that it was absolutely covered in lakes just before it collapsed. Ice shelves have crevasses in them. If water gets into one of those crevasses, the pressure of the water can cause the crevasses to expand, and if they then kind of penetrate through the whole ice shelf, then you can get sudden kind of collapses of the ice shelves.
Got it.
And we know this fairly well because it's one of the few ice shelf collapses we've been able to capture with satellite imagery, because it happened not so far in the past that we did have really good imagery of that. Now, Larsen C, Larsen B's next door neighbour, does have some of these lakes, but it's not so bad as Larsen B. There are some lakes up near the Antarctic Peninsula mountains, but they're not all over the ice shelf like they were with Larsen B. So the question I really wanted to answer when I was doing my PhD research was, well, how are these lakes forming on Larsen C, and should we be concerned? Are we going to get a Larsen B situation somewhere in the future? Because Larsen C is a lot bigger than Larsen B.
Oh, wow.
So that's extra bad news if we lose that ice shelf. So the paper is describing how we did that, but with maths, because why would you not use maths? That's the best way to do it.
How else would you do it?
Exactly. So in the figure 2 that you picked out, it describes some of the equations that we do that.
Now we have a model.
Yes, I think this is the time to bring in the model.
Excellent. So Alex, who's behind the camera, got very excited building a model. Actually, I'll move the actual ice out of the way.
Our science experiment.
Yeah, my coffee. Talk me through what have we got here in our model of an ice shelf?
Okay, so what Alex has done here is used darker coloured cardboard to represent kind of more dense ice. So if you think about an ice shelf, it's made up of, at the surface, kind of fluffy snow that's kind of freshly fallen. It's not very dense, there's a lot of air in there. And then as time goes on and more snow falls on the surface of the ice shelf, that ice kind of then gets compacted.
Right.
And as you go down, things get denser and denser until you get basically solid ice. So here we've got what is the kind of snowy, dense mixture, and
Yep.
down here, this is your ice.
This is not to scale, by the way.
The important part of the ice shelf that I care about in terms of water on the surface is that actually water can't make it all the way down to where the solid ice is quite often.
Okay.
Because we have something within this snow called the pore closure depth.
Because all the pores are closed.
Exactly.
So the density is still not ice,
Yeah,
but the water can no longer get through it.
exactly.
Okay,
and
love it.
that's kind of where I care about the ice shelf is
Got
down
it.
to this depth here. So water can be in here,
Love it.
can't get down there.
Yes, water, no water, ice.
Exactly.
What a model. I feel like we've got it all. How could it possibly get any more complicated than that?
I think we're most of the way there, but we're going to add some water in, which
Right.
does make things horribly complicated.
Okay, let me extend the ice shelf. Okay, so there's some more ice there.
Yeah.
All right. There's some more compacted snow there.
Okay, so here,
Uh-oh.
this now represents that the ice shelf is not completely flat. The general structure of the ice shelf is going to be fairly similar in that it's going to go from light fluffy snow
Yep.
to dense solid ice. But the surface of the light fluffy snow is not going to be the same across the whole ice shelf. The surface has different heights or topography. And where we get kind of low points in the ice shelf, that's where the water is going to accumulate when we get melting on the surface. Exactly. But for this to happen, we need to fill up all of the snow from the pore closure depth all the way up to the surface.
So this is pore closure depth here. And so that all has to be saturated with water
Yeah. And you're
until
kind
you
of
have this kind of
basically like
surface
an
water kicks in.
Yeah.
Got it.
Okay, and then when we have a lake, it can sit there on the surface, but because it's Antarctica and it's pretty cold, as well,
Oh,
you can just, I can't, but
real
you can tell me
cold,
it's
real cold.
Yeah, I'm sure you had an awful time.
I wouldn't bother going, it's awful. It's really good.
So these lakes won't sit there the whole year round. Eventually they'll start to freeze from their surface, just like lakes do here in the UK in the
Here
winter,
we are.
and then we get a lid of solid ice sitting on top of the lake.
So your research here, you're trying to work out what affects the heat transferring through this system, and then how that changes on some kind of time scale,
Yeah.
I guess.
Equation 1 in this figure is the heat equation. So it's just showing how quickly any energy changes in terms of temperature are transferred through this snow and ice.
And so we've got rho, I guess, for density.
Yep.
Tell me if I get any. Let me see if I can guess them all. You've got rho for density. I'm going to skip over C for a second. I bet that's some kind of constant for this type of ice.
We'll come back
Let's
to that.
skip
We'll
right
come
over
back
that.
to
Skip right over that. Okay, we then got a partial derivative of a big T is temperature, little t is time. So this is the rate of change of temperature over
so they're
time.
the main important part.
Excellent. You've then got another derivative with Z, which I imagine is the vertical direction, because I read the paper earlier and
Yeah.
it said that. And then K, K, now maybe that's the constant. And then you've got a rate of change of temperature over height.
Yeah.
Right, so what is C and K?
Okay. So C here is the specific heat capacity.
Right.
So you're right in terms of it's kind of a constant, and it would be
Yeah.
a constant for ice, but because this is an ice-air mixture, we have a complicated version of it where we have to combine the two of them depending on how much is ice and how much is air. which
Right.
changes as you go down into the ocean.
Okay, but that's how much heat it can absorb for a change in temperature.
Yeah,
Got it.
exactly. And then your K is your thermal conductivity. So that's going to,
And
be
that's
how well this
how well it
substance
transfers heat,
can
yeah.
transfer heat.
And so that equation will tell you if you've got heat at one end and not at the other, as time progresses, how it then distributes
Yeah.
itself through the mass. Okay.
Which is essentially what happens here, but the heat comes in at the surface, so that's equation 2, which is the surface energy balance. So that takes information
Oh, that's a
from
lot
things like
bigger.
weather stations.
Yep.
This one, it's not so bad, it's mostly adding up, to be honest. It looks a
Yeah.
lot complicated because there's loads of terms, but essentially anything in that that's an F is information we get from a weather station. So that's energy coming in from the sun,
Right.
things like wind speed, those make up all of those F values. And then again, we have a change of temperature, capital T, with depth Z, so that's telling you at the very top of your ice shelf what temperature gradient we have there. So now we've got some more layers.
Oh my goodness, yeah.
But I think the main things to look at here are equations 14.
So that's the
and
transfer
17.
from the lake into the snow.
Yep, and the changing
Seven-
of the ice. into
17
the
ice
lake.
into lake. Okay. What order would you like to do 14 and 17?
Well, they're both kind of similar because they're
Okay.
both something that we call a Stefan problem, which is essentially a moving boundary problem. So when we've got two materials in different phases, essentially how quickly that boundary between those two materials moves.
Ah, so you got liquid and solid,
Yep.
and the boundaries moving around as they melt or freeze.
Yeah.
And this is was it a Stefan problem?
Stefan problem, yes.
So 17, what do we got now? We got the density of ice. What's curly L?
That is the latent heat,
Oh,
which is the energy that is either taken in or given out when a substance changes.
because this is the phase boundary.
Exactly.
Right. Now you've got a change of HU over time. HU,
So HU is the height of the boundary.
and then that equals K, and that would be our the transfer, the conductive
Yep, the same K we had before.
K from before, temperature over height, and then you're adding on another F term.
So that's to do with energy kind of coming in from the sun. And because this one here, despite the fact that it's dark grey here, actually when you have ice on top of a lake, it's generally fairly transparent.
Ah.
So some of the sun's energy can still be getting through this.
Down to
and
this
into the
boundary.
lake. So it might still be heating up this lake a little bit, even though it's frozen on the surface.
And then I guess the 14 is the same deal, but for down here. So let's bring up
Exactly.
14. Okay, now up here we go. So this is 14,
Yeah.
which is very similar, but it's got this, is that a phi?
That is to do with the solid fraction, because this here is kind of this one here is a snow ice mix.
Right.
And has some air in there, so we need to account for that.
That's
It's
the
not
amount
solid ice
that's
like this
solid.
one. Yeah, essentially.
Got it. Then we've got rho for density again, curly L, and then everything else is the same.
Yeah.
Oh, you've obviously got a slightly different transfer going through the ice at the top,
Yeah.
but that's the same deal, just for a different, going through a different substance.
Exactly.
And then what happened? So you set up all these equations. Then what do you do with them?
So I coded these up originally in MATLAB.
Yep.
I've now converted it into Python, so it's
Oh,
open
nice.
access, and people that are really into ice shelves can look at it.
Should we link to those below if people want to?
Yes, we can
We'll
absolutely
link
do
to
that.
Sammy's way better than my
You want to have
Python
a play
code
around?
below. Yeah. The viewers for my channel are used to a real low standard when it comes to Python code,
Okay.
so this would be a welcome example of good code.
So yeah, coded this up, used information from all the station that was on the Larsen C ice shelf, and then we made some lakes, which was exciting. But one thing we did notice, when water gets into this snow here, it will percolate down and it will refreeze and it will release heat, and that means that this kind of whole area of snow starts to heat up. But because the snow, once we get down so far, is quite cold, it's actually going to take quite a lot of water refreezing to bring it up to that temperature,
Right.
rising temperature. And when you have a lot of water refreezing in one place, we suddenly get a very dense layer of ice. Before we even got down as far as the pore closure depth, we were getting these kind of really solid layers of ice just forming within the snow. And we were quite confused at first. Honestly, it looked a bit like a numerical instability.
Right.
So I spent a lot of time checking that it wasn't numerical
That's bad.
instability.
That's
Yeah, so that's when essentially you're solving equations in a way that you shouldn't be.
so you're like, our equations have gone wrong. They're predicting this weird stripe of ice.
Yeah, but once we'd investigated them and it turned out, no, they were really there. They weren't just maths going wrong. At a similar time that I was investigating this and being like, okay, well, I've got these ice lenses. A group from Swansea and Aberystwyth universities were down on Larsen C doing some field work, and they actually dug up some of these ice lenses. And I was like, wow, this is what my model has been predicting thousands of miles away.
Okay, so I mean that's incredible, and don't get me wrong. Just from a maths point of view,
Yeah.
being able to predict reality and then reality matching the equations, deeply pleasing. But why do we care about these ice? Like, what's?
Yeah, and that's
I assume
that's
it's
just
got
as
no
important, I think.
impact on us whatsoever.
Well, Antarctica is pretty far away.
I know.
So
It's,
yeah,
it's
you
not
do
quick to
know,
get
I
to.
don't know, we've been there.
Yeah.
But even the changes there can affect us, and that's because of sea level rise. That ice that's melting and getting to the ocean is then going to be spread out over all of the oceans all over the planet,
Yep.
and that is of course going to affect us pretty much wherever you are in the world. Either you're on a coast and it's going to affect you directly,
Yeah.
or you're going to be affected in other ways. For example, all the people who are currently living on coasts having to move to places like Reading.
Yes. Now, if I want to bring back in our our beverages.
Yeah, because we've mentioned sea level
Yeah.
rise, and that is one of the key things that we do talk about as glaciologists and scientists that study this area. When people say, like you just did, why should we care?
Why should we care?
Sea level rise is the obvious one. Because there's between 50 and 60 metres of sea level locked up in Antarctica currently.
Oh, we had effectively a small ice shelf in a glass,
We did.
and it's been melting, and we marked where it was. Now, I don't want to say you're scaremongering, but I'm looking at this, and the water level hasn't changed,
No,
despite my ice shelf melting.
Exactly.
Explain that, scientist.
Okay, it's already displaced its own weight in the water, so when it melts, it's not adding anything to the water that wasn't there already. We call this Archimedes principle. So this is something we've known about for a very long time. The problem is, as I mentioned earlier, those glaciers, you asked what happens to the glaciers that used to feed onto Larsen B, they used to be held back by the ice shelf.
Right.
So if we had a glacier here, it was going down onto the ice shelf, it would flow onto there, and little bits of the ice shelf would break off and break into the ocean perfectly naturally all of the time. That's how we get icebergs. And this is kind of a system. We have ice coming in from Antarctica, adding to the ice shelf, and some breaks off the end. But if the ice shelf itself is kind of holding this glacier here back, if we take this ice shelf away,
So that's gone.
there's nothing to hold this one back, and it can just
Straight into
speed
the
up
water.
and go straight into the ocean.
Got it. So all the ice on Antarctica, of which there's a lot. I was told when I was out there, they said it's like 2 kilometers thick.
Yeah.
It's just ice.
Even these ice shelves that are the bits that float off the edge can be tens to hundreds of meters
It's
thick.
insane. What are you working on now? Where's the
so
SAMI effort going these days?
I am still working in this. So this model was really looking at kind of the vertical processes on ice shelves. So what's happening at the top and where the water is going down.
Do you describe it as like it's a one-dimensional model?
Yeah. But of course, ice shelves, as we said earlier, they're not completely flat. These lakes are only going to form in kind of lower points on the ice shelf surface. So I made the model 3D. And that's what I've been working on since then.
Amazing.
Just adding in more maths, making it more complicated.
I love it.
Making it more accurate. Which is
So now you can 3D model it and then run that over several seasons
exactly.
and follow how everything changes and evolves.
Yeah.
I would just like to add that yes, I keep saying you've not been to Antarctica, but while Sammy has not been to the southern pole, you have been to the Arctic.
Yes, I've been up to Svalbard a couple of times, so that's an island north of Norway.
That's a long way up.
Yeah, that was really exciting. And this summer I'm going to Greenland for the first time.
Ah.
Don't tell me you've been there already.
I've not been to Greenland.
Okay,
I've been to Svalbard, but I've
Okay.
not been to Greenland. You're out in
Good
front,
place you
yeah.
haven't been to. So
No, I'm very envious now.
yeah, this is going to be really fun. I'm going to be a real glaciologist on the ice. Not that modelers aren't real glaciologists, obviously. We're
but-
possibly the most important glaciologists, I would say.
I would say too.
But it's also sometimes quite nice, I think, to see the things you're trying to model. So
Yeah.
I'm going to be spending a portion of my summer in Greenland actually like camping out near the ice sheet, going out, taking measurements of water on the surface of the ice shelf, and thinking about where that water's going as well.
If you would like to experience Antarctica as well, I will link to the Hurtigruten trip that I went on below. They're not sponsoring the video, but it was absolutely amazing. Huge thanks to the Biscuit Factory in Reading, who let us come and film in their cafe. And of course, thanks to Sammy Buzzard for doing such fantastic mathematics and being prepared to talk to me about it. Links to her code and other details below.